Hello and welcome to our lesson today on plastic analysis of slab using the E-line method. So in today's lesson, we are basically going to solve some tutorial questions. Haven't gone through the theoretical aspect of E-line analysis in our class. What you need to remember is that E-line analysis is a method of plastic analysis, and that method is an upper bound method that is used to analyze mostly reinforced concrete or steel slab. So let's go straight to the tutorial questions. We are going to look into the tutorial question. The tutorial question here is given. You can see a rectangular slab has been given of dimension 7.5 by 9, and in this slab the heel line pattern has been supplied already. So you can see the blue line here are the heel line, sacking heel line pattern, the blue solid lines, while the dotted line, green dotted lines here at the continuous edge are the walking heel line pattern. Let's look at the question. The question says for the above slab, AB and BC are continuously supported, AD and CD are simply supported. The slab carries a design unit ultimate UDL of 20 kN per meter squared. Assume that the slab is reinforced with the same area of steel in both directions, that is top and bottom, such that the moment capacity in each direction is M. For the assumed pattern of yield line shown above, that is sacking equals to solid line, hooking equals to dashed line, calculate M. M there is the moment capacity of the slab. Also, calculate the value of M for two additional yield line patterns and state the value of M you will use in practice, giving reasons for your choice. Now, in this first one, the heel line pattern has been given unto us. So what we are doing, we are going to go ahead and analyze this slab based on this pattern that have been given, and then assume our own pattern in two other patterns, and also calculate the value M. So for us to do this, remember from the question we are told that AB and BC are continuous. That is why you have hooking yield lines. You only have hooking yield lines on continuous or fixed edges. Now this vertical, the black line here and here, they are not yield line pattern. It is just used to divide this into shapes, into simple shapes. We don't want to deal with trapezium. So by introducing this line, this portion has been divided into rectangle, into triangle, rectangle, and triangle. So that is the purpose of that line. So we are going to go ahead now and solve our tutorial. So this is a solution to that question number 1. I'm just going to go ahead and explain it. This is the yield line that we have been given already, and we have been given the yield line pattern of the slab already. Nothing has changed here. So what we are going to do is to go ahead and calculate the external work done and the internal energy dissipated by this yield line. So first of all, we go ahead to calculate the external work done. The first thing we do is to assume the point of maximum displacement. This line PQ is basically the point of maximum displacement in the sacking yield line. So we assume a unit displacement. That means we assume a value of 1, so that other forms of displacement will be taken from with reference to this particular point. So we go ahead and calculate the external work. We are going to do it plate by plate. We have 8 plates here in this rect slab. We have plate 1, plate 2, plate 3, plate 4, plate 5, plate 6, plate 7 and 8. So what we are going to do now, plate 1 and 2 are triangles and are similar in dimensions. And so we are going to calculate 1 and then multiply by 2 to take care of that. So what for plate 1 and 2, we are going to calculate external work. Remember, work is force times displacement. So that's why we are using N delta, where N represents the force and delta is the displacement. Now for the plate 1, what is the force? For us to get the force, which is like the load, in this case, we are going to calculate the planned area of the plate and multiply by the uniformly duplicate uniform UDL that we were given to be 20 kilonewton per meter squared. So let's go ahead. For triangle, what is the area of a triangle? Half base times height. So what is the base here in this triangle? The base is 7.5. So half of 7.5 multiplied by the height of this triangle, which is 3.75, multiplied by the UDL, which is W. Now for us to get the displacement delta, we look into the triangle. This is the triangle. This is the base of the triangle. So that is where the rotation takes place. So if this maximum place of displacement is 1, the centroid of this triangle is at the point 1.1 over 3 from the point of rotation, and the displacement will be measured at the centroid. So 1 over 3 multiply by 1, which is the place of maximum displacement. So that is why we have 1 over 3. But if you get confused, the simplest way is whenever you have a triangle, you use 1 over 3 as delta. Whenever you have a rectangle, you use 1 over 2 as your delta. So if we know what W, here the UDL is 20 kilonewton per meter squared. So if we substitute that, our N delta will give us this, which gives us 73.75 kilonewton meter. So we have calculated for plate 1 and plate 2. Now you look at plate 3, plate 4, plate 5, plate 6 are also the triangles and are similar in dimension. So we are going to calculate them together. So we now say in plate 3, 4, 5, 6, what is our N delta? If we pick 3, the N there is a planned area multiplied by W, that is which is our UDL. The planned area is half base times height, which is half of 3.75 times the height, which is also 3.75, multiplied by the UDL, which is 20. And our delta, remember, for this is triangle, our delta is 1 over 3. And so when you calculate that, you have this 46.875 kilonewton meter. What is now remaining is plates 7 and 8, which are also similar. They are rectangles and they are similar in dimension. So we go ahead and say in plates 7 and 8, our N delta, again we calculate the planned area. The planned area, this is a rectangle, so the area will be base length times width. And let's say the width here is 1.5, which is this place, and the length is 3.75. We multiply by our UDL, which is 20, and because this is a rectangle, our delta is 1 over 2. So we have 56.25 kilonewton meter. Now for us to have the sum of external work, that is summation N delta, we go into this. Remember, for plate 1 and 2, we have 93.75 multiplied by 2 because those were 2 plates. For plates 3, 4, 5, 6, we had 46.875, so we multiplied by 4 because there were 4 triangles there. Then for plate 7 and 8, we had 56.25, so we multiplied by 2. By the time we have sum all these things together, we have 487.5 kilonewton meter as our summation N delta. So the next thing we go to do now is to calculate the internal energy. Internal energy is actually the energy dissipated by the heel lines, by the Hawking and the sacking heel line. So first ahead we go for the Hawking heel lines. There are two Hawking heel lines at AB and BC because those are the continuous edge. And the formula for those heel lines is ML theta, where M is the moment capacity. In this case, it is unknown, and L is the length of the heel line, and theta is the angle of rotation. So we go ahead for heel line AB. Our M is unknown, but our L is 7.5 because the length of the heel line is 7.5. So that's why we have 7.5 in. Now, our theta, to get our theta, we always measure it based on the point of maximum displacement. The point of maximum displacement in this case is PQ, which is this place. And where is the base of rotation? The place of rotation is this line AB. What is the distance between that point of maximum displacement and the base? That distance is 3 over 7, 3.75, which is this. This theta we calculated is this, and this theta one now. So because we know that this point of maximum displacement is 1, and theta here is like saying tan theta. And remember, for very small rotation, tan theta is the same thing as theta. So we can say that theta is opposite over adjacent. In this case, opposite is 1 and the adjacent is this 3.75. So we have our theta to be 1 over 3.75. Again, just like delta, if you get confused, the simplest way to do it is once you get the distance between the place of rotation and the place of maximum displacement, just do 1 over that distance. So that will give you 1 over 3.75. So by doing that, we have the Hawking displacement at AB is what? 2m. We do the same for Hawking line BC. If we go to Hawking line BC, the length is 9. And this distance again is what? 3.75. So we can go ahead and say that ML delta is 9m. 9 here is L. Then theta in this case is also 1 over 3.75. So we had 2.4 m as the Hawking heel lines in BC. So the next thing we are doing is to calculate the sacking heel lines. If you look at their side, there are sacking heel lines. The sacking heel line here is AP, BP, DQ, Q, CQ, and PQ. There are 5 sacking heel lines, and 4 of them are the same. AP, BP, DQ, and CQ are the same. So again, if we calculate 1 and multiply by 2, it will save us the whole trouble. So we pick AP, heel line AP. So the first thing you need to know, this is heel line AP. For us to calculate this heel line AP well, we are going to find its vertical and horizontal component. This is the vertical component, which is this line. The horizontal component is like this. So we are going to calculate, instead of this diagonal, we are going to calculate for horizontal and for vertical components. And that will give us the heel line from AP. So we go ahead and calculate for the vertical component, which is from here to here. Our M is unknown, but our L here is 3.75. So we have that ML here. That is why we have here that ML is actually 3.75 because we are doing the two the same side. So we have factorized M. M is factorized. So what we have inside here is actually L theta. So for the vertical component, L is 3.75. For the horizontal component, it is the same thing. L is also 3.75. For the vertical component, the distance between the point of maximum rotation and the base of rotation is also 3.75, and is the same in the horizontal component. So theta for both of them is 1 over 3.75. That is why you have here 1 over 3.75 for the vertical. That is theta. You also have theta here as 1 over 3.75 for the horizontal. So by the time you multiply all of them, you have 2m. And also remember that there are 4 of them. So here, like, remember we say this is equal to this, is equal to this, equal to this. Remember that. The next here line is PQ. Here line PQ. Again, we are going to calculate because it causes rotation both on the upper plate and on the lower plate. So we are going to calculate for both. That is why we say the first thing, remember, is ML, the ML the theta. And our M here is 1.5. So when we go there, for the upper plate, we have that M is unknown, L is 1.5. And if you look at what is our theta, this is the place of maximum displacement, this is the base, and that distance is what, 3.75. So theta is what, 1 over 3.75, and it's the same thing up here. So that is why we go ahead and have our theta to be 1 over 3.75 for the upper plate, and for the lower plate we have the same thing, 1 over 3.75. So when you calculate all this, we have 0.8 m. So the next thing we are going to do is summation ml theta. This is actually summation ml. L is missing. Ml theta, that is the sum of the internal energy dissipated by both the Hawking and sacking heel line. So we go ahead and do that for AB. Remember, it was 2m, but there are 4 of them, so we multiply by 4. For the, which one is 0.6? Let me find out. 0.6. Okay, this one PQA. This is for the Hawking heel lines. This is for the Hawking heel lines. This is 0.6. I think we had 0.8. There is a little, could be an issue there. Let me find out. Okay, so our summation ML theta actually had a little mistake in this place. This is supposed to be 2 times 0.8, which should be 1.6. But whatever is the case, the value might be wrong, but the pattern is okay. So our summation M delta, if we do that, this place should give us 14m. And so you can go ahead and correct that. So how we got the answer, we have got our summation ML delta, ML theta, and we also have calculated our summation N delta. So when we use the principle of virtual work, we say the sum of external work done is equal to the sum of internal energy dissipated. So that's why we have summation M delta equals to summation ML theta. So that gives us this equals to this. And this is in terms of M. So when we make M the subject formula, we had this 36. If you're using the right 14 here, you should have 34 point something. So you can go ahead and use your calculator and do that. So by so doing, we have been able to calculate the value of M for our first heel line pattern. The question has said that we should go ahead and calculate for 2 other heel line patterns. So the next heel line pattern is this one. We had assumed our heel line pattern. So look at the heel line pattern here. It's similar to the first one, but there are some changes in the dimensions. In practice, walking continuous edge usually have bigger plates. Usually repel heel lines. That's why you can have this side 4 meter, while this other side 3.5. This side 4 meter, this other side 3.5. So with this, is similar to the first one. The only thing is change in dimension. So we can go ahead and calculate for external work. In this case, plate 1 and plate 2 are not the same. All the plates are different. So we are going to calculate it plate by plate. So you can see for plate 1, we have our n delta is half base times height. What is our m delta is, okay, n is area, which in this case is half of 7.5 multiplied by 4. The height is 4. So you have this 7.5 over 2 multiplied by 4, multiplied by the UDL, which is 20. And our delta here is 1 over 3 because it is a triangle. So that gives us 100 kilonewton meter. For plate 2, which is here, if we do similar thing that we did to plate 1, which is here, we had 87.5. For plate 3, which is also a triangle, area is half base times height. What is the base? 4. So you have here 4 over 2. What is the height? 4. You have here. Our UDL is 20, and because this is a triangle, our delta is 1 over 3. So that gives us 53.53. So if we go ahead and calculate for plate 4, follow the same pattern, calculate for plate 5, we had this 46.67. For plate 6, we have this 40.83. Plate 7, remember plate 7 is a rectangle. So what is the area of a rectangle? Is this length, which is 3.5, multiplied by the width, which is 1.5. So that's why for plate 7 you have this 3.75 multiplied by 1.5 multiplied by the UDL, which is 20. And because it is a rectangle, you multiply by 1 over 2. And it gives us 52.5. The same thing was done for plate 8. And we have our n delta to be 60. So by the time we sum all the n delta, we had 48.487.5 kilonewton. Is that what we had in the first case? I think, yeah, we have the same 487.715. So it's the same thing. Despite the changes, we had the same external work done. So we go ahead to calculate the internal energy following the pattern. Remember, even in this heel line pattern, we still have two working heel lines at AB and BC. And for working heel lines AB, our ML theta is, what is our L? L is 7.5. This is 7.5. And what is our M? M is unknown. And our theta here is 1 over this distance. This distance is 4. So that is where we have our theta to be 1 over 4. What about working heel line BC? We go to BC. The BC here, the length is 9. If you add all of this, it will give you 9. The length is 9. And our distance from the maximum displacement is also 4. So that is why you see working heel line, the 9m multiplied by 1 over 4. So this gives us 2.25. And okay, meanwhile, this value here is 1.8. Okay, 1.875. This place is 1.7875, so you can go ahead and write it down. So having done that, we go to sacking moment. We calculate our sacking heel line. In this case, all the sacking heel lines are different, so we calculate it differently. So let's pick which is the first one, AP. Let's pick AP. AP here will have the vertical component and the horizontal component. So let's go ahead and calculate it. For this vertical component, our L is 3.5 and our theta is from here to here is 4. Our theta is 1 over 4. But for the horizontal, and also for the horizontal component, our L is 4 and our theta is 1 over 3.5. So that is why if you go here to AP, you will see 4m multiplied by 1 over 3.5 plus this other component, which is 3.5m multiplied by 1 over 4. If you do all of them, it gives you 2.02m. If you go ahead and do for the rest of these diagonal here lines, which you find the vertical component and the horizontal component, it gives you all these values. And then remember that for this, you're going to do for the upper plate and for the lower plate. You're going to do for all of them. So by the time you find the sum of summation ml theta, add all these here line. Remember 1.875 here at Hawking here line AB. So when you do all that, it gives you summation ml theta equal to 12.965 m. And also using the principle of virtual, always remember to write this. Writing this gives you at least half mark in case of exams. So when you do this, you now equate this to this. By calculating from M, you had 37.6. That is for year line pattern 2. This is a third year line pattern and is still similar. The only difference is this place you have 4. This middle one, instead of 1.5, you have 2 meters. Now it's always left for you to assume your heel line pattern. And so this heel line pattern was assumed. So if you follow the same principle of calculating the external work, in this case summation M, N delta was 500 kilonewton meter. And also calculate for Hawking heel lines and for sacking heel lines, in this case summation ML theta was 13.315. So if you do that, use the principle of virtual work, which sum the external work to the internal energy, that makes this equals to this, and by calculating M, we have M is 37.55. Now from the 3 moment capacities calculated, we have had 3 different values. We have had 37.55, this other one 37.6, and this other one 36.93. So which one will you choose in design? He said from the 3 moment capacities, I will choose 37.5, the lowest. 37.5, is that really the lowest? The lowest is actually 36.93, in which if you do the correction of making this place 14, I think it will be lower. You'll be having 34 point something. So this is actually the lowest. So what you will do in your work is that from the 3 moment capacities, I will get that value, whether 34. That is the lowest. You always choose the lowest because yield line analysis is an upper bound approach of plastic analysis. So that is the reason when you solve the 3 yield line pattern, choose the smallest value. That will give you a safe analysis. So that is it for our tutorial question 1. That is a solution for tutorial question 1. And I would like to say thank you for watching to this stage. Look out for the next video, which you will have solution for tutorial question 2 and tutorial question 3. Thank you very much.